nice break. We're going to go ahead and get started now. So we're going to get started with a very interesting talk here from Ross Miller. He's going to be presenting efficient metadata scanning using ZFS and NVMe over fabrics. So Ross is a software developer at the National Center for Computational Science at Oak Ridge National Laboratory in Oak Ridge, Tennessee. He has BS and MS degrees in computer science from Baylor University. He has worked on everything from embedded microprocessors for avionics up to the largest supercomputers in the world. He has been with NCCS for about 12 years, working on a variety of projects, including file systems and telemetry monitoring for supercomputers. I'll go ahead and hand it over to Ross.
Again, good afternoon, everyone. My name is Ross Miller, and I'm going to talk about some interesting work that we did over the last few months ago, looking at trying to use ZFS and particularly ZFS snapshots to scan the metadata for our Lustre systems. Now, first things first, this is a prototype. We have not implemented this in production, and we probably won't, as you will see why as I get on with this presentation. The basic idea, what do we want to do? Why do we want to do it? We want to know what's going on our file system, or file systems, plural. How things are changing, how big are files, how many files are there, how, all kinds of stuff like that. We've tried to do some of this in the past in various ways. Historically, these techniques just haven't scaled very well. Yeah, you can run find from a client, but that's going to take hours or days, and it's going to load your metadata server. LFS find is a little bit better, but still really not fast enough. We looked at using the Lustre change log, and we had problems with that can't really keep up. And if it gets out of sync, now what do you do? Because once you've lost it, you can't just start over from scratch and rescan everything. And lastly, and one of the interesting things, and I'll touch on this in a little more in another slide, but none of these techniques actually hold the file system in a consistent state while you're scanning it. So that has some implications for how you actually analyze the data later. It's like, well, how many files were in this directory? Well, we're not really sure because somebody was busy deleting it while we were deleting files while we were doing the scan. So in general, the basic idea from this was we want to efficiently and quickly scan the file system. In our case, quickly translates to, give it an hour. Honestly, we could get by with something that even took a full day to do, but an hour would be nice, once an hour. And we don't want to overload the metadata server. We don't want these operations to noticeably slow down normal, file system usage by our users. That's not acceptable. The users would obviously start complaining, and we don't want to have that. And the ability to do incremental scans are preferred, and in fact, probably necessary just to be able to meet the first two goals. But we do need to be able to do a full rescan if we ever manage to get out of sync with the incrementals for whatever reason. So with that in mind, we started looking at ZFS snapshots. These looked particularly like they had a lot of potential for us. In general, ZFS snapshots, they're very low cost to create and destroy. When you do have them around, the only space the snapshot takes is space for the changes, it's not like you're making a whole copy of the file system or anything like that. Since they are snapshots, we now have a nice consistent view of what the file system was at a particular time. That's again, when you go to actually analyze your data, that's a really nice thing to have. And then lastly, there is a tool called ZFS diff that will report differences between two snapshots. So this all sounds really promising. But of course, there's a great big caveat. And the caveat is, yeah, it actually doesn't work. In order to run ZFS diff, the ZFS file system has to be mounted. From the point of view of ZFS itself, the file system has to be mounted. And Chris Brumgard in the previous talk kind of touched on this, but Lustre talks directly to the ZFS layer, but it does not mount the ZFS file system from ZFS's point of view. ZFS thinks these things are the various ZDEVs are not mounted unless you can't just go run ZFS diff. How we got around this was a little bit of sort of crazy thinking, but we have NVMe over fabrics. We can make those devices that are the ZDEVs appear on other servers, on more than one server. And that's what we actually did. We ended up using the NVMe over fabrics to make that device appear on a separate server and mounted it there while the MDT was still using it and while Lustre was still in operation. And that, of course, has all the operations people, as opposed to the researchers, just shaking their heads and cringing right about now, I assume. But we did actually get it to work, and I'll talk about what we did and how we managed to not destroy the MDT in the process. So just a quick overview of the test system I have set up. I believe my mouse pointer should be showing. So if you look at this center column, this is just a very simple Lustre file system. We have two OSSs, one MDS, one MGS. The devices themselves were in separate servers. And then the magic or the insanity, depending on your point of view, is this little bottom blue line where we take this single NVMe device that is being used as our MDS and mount it in a separate place on a separate server. So this test node is where we ran everything. In addition to having the device mounted over NVMe over fabrics, it also is just a regular Lustre client. And you'll see why. And this note about Kafka messages, the end result of all this analysis is to parse the files, parse all the metadata, format it as a Kafka message, and send it out to a large Elasticsearch cluster, or at least that was the idea. So that's why the output from all this is Kafka messages. So what we actually do, and this is how this is where it gets weird. Just using the standard Lustre tools, LCTL snapshot create, you create a Lustre snapshot. Then you import it, being very careful to use the read-only flag on the zpool import. Once you've done that, you're in pretty good shape. You can mount your file system. You can also, from the Lustre side of things, mount the Lustre snapshot, and we'll see why in a minute. And then step 5 here, we run ZFS diff on the 2 snapshots. This is the read-only pool that we've imported. ZFS diff just gives us a list of, this is all the files and directories that have changed. It doesn't tell us too much other than it's a file has changed. It'll tell us added, deleted, or modified. For files that have been modified, the idea is, and the very simple testing we did, have a script that parses the ZFS diff output and then stats all the modified files using, and that is why we actually mount the file, the ZFS snapshot in step 3. Step 4. So you parse the output from ZFS diff, stat the files, anything else you wanted to do at the time. We were considering doing some pre-processing, basic calculations, and then in our case, push everything out to Kafka and Elasticsearch. and the reason for that was for analysis, later on. Once you're done, just unmount Lustre, unmount the ZFS file system, export that Z pool, and then you can delete the old snapshot, although I kind of glossed over this, but in order to diff, you need 2 snapshots. So the idea is take one, if you're doing this every hour, take one, diff it against the one you took the hour before, get your results, and then you can delete the oldest of the snapshots since you don't need to keep that around anymore. But you do, since it's a diff, you do need 2 snapshots to delete or to actually work. So the big question, how do we make sure we don't trash the metadata server? That's really important. The good news here now is, as I said before, zpool import has a read-only flag. And we did double check with the developers and also confirmed by inspection of the ZFS source code. When you specify that read-only flag, ZFS does in fact open the devices themselves at the Linux system level. The open call is using read-only. So there's no way for ZFS to actually write anything or modify those devices in any way. So that's kind of why this is all possible, even if it is slightly crazy. We did actually consider, I had a suggestion to look into using C groups to add an additional level of safety in case something ever happened in ZFS and they decided to change the behavior of the read-only flag. We could theoretically set that device to be read-only and have it enforced by C groups. I have not tried this. That was a suggestion that came kind of too late for me to make it to try this out and get it into this presentation, but it is something we would look at in the future. As for performance, as I mentioned in that early slide, this is a very small test system. Each VDEV was a single NVMe device. When I went to go diff the two snapshots, we were able to get about 1,900 files per second out of ZFS diff. That pegged the CPU, and it looks like ZFS diff is a single threaded tool. So we could only use one CPU core. As far as stats go, we were able to do 11,000 a second. So that was no problem. And our Kafka message ingest rate was better than 50,000 a second. And that was without actually much in the way of optimizations, because at this point, it just didn't matter. The combined diff, stat, and then publish a message were limited by the performance of ZFS diff, 1,900 files per second. And we chewed up 1 1/3 CPU cores to do that. There's a question about whether this is actually scales up enough. The ZFS diff being the limiting factor, 1 thread, 1,900 a second comes out to about 6.8 million changed files that it could process in an hour. As I refer back to my one of the original goals was try to do a scan once per hour. In a file system with something like 5 billion files, which is not out of the question for what we're looking at, in our next file system. I don't think we've hit that with our current file system, but for these, that's kind of the range we're talking about at ORNL. If you got 5 billion files, being able to scan 6.8 million an hour, that's only 0.13%. Kind of hard to say if that's really sufficient or not. And talking with some other developers and colleagues, it seems to probably depend on what your users are actually doing. Some codes that write small numbers of large files, that's fine. It's the limiting factor is how many different files have changed, not how many bytes have been written or anything like that. So if you write 1 terabyte to one file, that just shows up as one change in the diff, and that's no problem. If your codes write a bunch of small files and that 1 terabyte of written data is spread out over 1 million files, that is going to obviously result in a much greater number of files and number of lines of output in the diff that need to be processed. So yeah, whether ZFS diff is fast enough is an open question. We're not really sure. We don't really have any data to support it one way or another, just some kind of gut calls that it kind of looks iffy. How am I doing on time? One other thing I wanted to touch on, we are statting every single file, or well, the vast majority of the results from the ZFS diff output will be modified files, and all of those get statted. Since the ZFS diff operation itself is the limiting factor, that doesn't seem like we really need to worry too much about overloading the metadata server, but there's no reason to put any more load on it than we have to. And in particular, and the point of what I'm getting at is that for our applications, the lazy size on metadata would be probably perfectly fine for our purposes. Fortunately, this has landed in Lustre 2.12. The downside is trying to get Lustre to reply to a stat request with the lazy size instead of the actual size. That's a little trickier. There's a patch available that allows you to do that using the statx function call. That'll be in 2.14. So that's some possibility going forward for us. These tests we did originally just used the full-on regular size, and thus, the loaded the metadata server a little bit more than that probably really needed to be. And then one other thing I wanted to touch on is this whole idea of incremental scan versus full scan. As I said earlier, this technique relies on having 2 snapshots. You have to have 2 to diff. So if we ever get out of sync or need to do a full rescan, how do we do that? And it turns out a pretty simple workaround, as long as you have a little bit of forethought. Right after you set up the Lustre file system, take a snapshot and keep it around forever. At that point, if you ever want to do a full rescan, you just diff, instead of diffing the current snapshot and the one from an hour ago, you diff the current snapshot against this baseline. And that gives you all of the changes since you originally set up the file system. So that seems to be a pretty easy way to go, as long as you think in advance and actually create that snapshot. Since the file system is empty when you create this base snapshot, of course, there's basically 0 cost to keeping it around. So thoughts and conclusions. Normally in a presentation like this is the slide where the author talks about how great all the work is. In my case, I'm going to spend some time talking about all the reasons why we probably won't be using this technique, at least not in production. One problem is the design, as I've just discussed, kind of only works for some fairly niche use case. You do need, since we're relying on NVMe over fabrics, that means you need NVMe devices. Since we're relying on ZFS diff, that means you need ZFS. In addition, as a corollary, you also need networking that supports NVMe over fabrics. You need to be, or there's no point in doing this unless your system is large enough that other methods won't work. And finally, you need to have a system where your normal workloads aren't limited by the IOPS available, because that is one of the things that this system is going to put some heavy load on the device that is being diffed. And it's going to use up a fair amount of the available IOPS. In our particular case, it looks like our system, like the system we're likely to be having in the near future, would meet all of these requirements. But we're kind of a unique case. There aren't too many other places like ORNL. And then the other one, and this is what got an awful lot of our operations people pretty nervous. Actually trying to do this in production would be perilous. If you forget to put that read-only flag when you do the import, ZFS might go and make some writes to it and result in corrupting your metadata server. That's a really bad thing, and nobody wants that to happen. So that made a lot of people really nervous when we talked about it at our operations level. It was also unclear if we could ever prove that this technique is safe. Clearly, it's not something ZFS was designed for. The best we would be able to say was it didn't corrupt the MDT during this test, but no guarantees further on, or at least it'd be very hard to say that from further on, it would never happen. So that also made a lot of people very nervous. So in the end, when we were talking about this with our operations people, we decided that the risk versus reward just wasn't there. It's a lot of risk to take on to get some data that we either didn't need or had other ways of getting the data that we really did need. So yeah, we decided probably not going to do this, deploy this in production. For all that's interesting research. So just some, in closing, if we're not going to use this technique, why am I sitting here talking about it? Why are you listening to it? For one thing, like I said, it's pretty interesting work, and I was very interested to see if we could actually make it work. More importantly, I'm hoping this will spawn some discussion, particularly at the ZFS side of things. For example, if we could remove that requirement to have the ZFS file system actually mounted in order to do the diff, all of a sudden things get an awful lot easier. You don't need to dual mount the system. You don't need, and that means you don't need NVMe over fabrics, and that means you don't need NVMe. So things get a lot less niche and a lot more usable. The other thing is also, it seems like ZFS diff could probably be, the performance there could probably be improved, or at least should be looked at. I'm sure that's not, has not been a high priority for the ZFS developers, but I was doing testing where everything was coming out of the read cache. It was all coming out of memory, and we still only got 1900 files per second. So I got to believe we can go a little bit faster than that if somebody just actually wants to take the time and look into that utility. This concludes my remarks, my presentation. I would like to acknowledge Oak Ridge Leadership Computing Facility. They're the ones who pay me and make this all possible. Thank you for paying attention.
Thank you, Ross. So there was some questions about harm with the ZFS snapshots, but I think Andreas resolved from Patrick. There was a discussion about Lustre changelogs, and the comment that was made that they aren't able to keep up. Maybe you can quickly elaborate on that. We've got about 2 minutes left here.
So we have had problems with them not being able to keep up. I don't know what, I don't know where exactly what the question in the chat was about, but we have seen cases where it's just running behind. What the changelog is reporting is changes that had happened a while back. And then again, if you're trying to then parse that and do something with that data and get that data into a database like Elasticsearch, what do you do if you've gotten behind and now your file system doesn't match anything at all about like what the changelog is actually reporting? So that was, yeah, we have looked at it, but we couldn't really make it work.
Yeah, I think changelog consumption is always a nice topic of discussion. We can probably carry that one over to the social event afterwards. Let's see, there was another question regarding snapshots consistency. On some file systems, a snapshot image of a file system would look like a crashed file system. That means some recovery of any journals would need to be performed. This makes a true read-only behavior hard. That's why I was asking. I think that's probably specific to a file systems implementation, but I will not answer for you.
I'd be curious to know what he means of it looking like a crashed file system. From ZFS's point of view, it looks fine when it's mounted read-only. I'm a little unclear on what the questioner is asking there.
Sure, Michael, why don't we take that one offline and we can follow up either with us or with Ross directly. Okay, it looks like that's about it. So thank you very much, Ross. I appreciate your time.
All right, thank you.